Let's learn everything we have to know about E1 and E2 reactions. E1 and E2 reactions are elimination reactions. And in these reactions, we will start with a substrate that has a leaving group, something that has a leaving group, for example, a bromine. And after we do E1 or E2 reaction, we will end up with a double bond. So elimination reactions, E1 and E2, get rid of the leaving group and produce a double bond. Unlike substitution reactions, SN1, SN2, which replaced the leaving group with the nucleophile, in E1 and E2 elimination reactions, we get rid of the leaving group and we make a double bond. Let's go through each reaction thoroughly, learning how to do the mechanism, how to recognize it, and how to predict the product, starting with E2. E2 reaction is a one-step reaction. In this reaction, the leaving group leaves, and I have a list of good leaving groups here. It's usually iodine, bromine, chlorine, OTS, OH2 are also good leaving groups, but usually we have halogens such as iodine, bromine, and chlorine. So in this reaction, leaving group leaves, so we draw an arrow from the bond between the leaving group and carbon to the leaving group, showing that this bond is breaking, giving electrons to the leaving group. And at the same time, base is going to take beta hydrogen. Beta hydrogen is a hydrogen that is attached to a carbon neighboring the carbon with the leaving group. This hydrogen will not be shown to us. We will have to draw it out ourselves. We will have to find all of the neighbors of the carbon that has the leaving group, look at their hydrogens, draw the hydrogen out, and draw an arrow from the base to the hydrogen, and finally the third arrow from the bond between hydrogen and carbon to this bond to make a double bond. Double bond will be created between a carbon that has the leaving group and its neighboring carbon. Now for SN2 reaction, for E2 reaction, and we will go into this more deeply. The leaving group and hydrogen have to be on opposite planes, which is called anti-periplanar. If they're not on opposite planes, E2 will not occur. So what that means is, if leaving group is on a wedge, my hydrogen has to be on a dash. If leaving group is on a dash, my hydrogen has to be on a wedge. If leaving group is up, hydrogen has to be down, and so on. Now, if the hydrogen that you're trying to take off is not in the opposite plane of the leaving group, you will have to rotate around the bond until it is. And if the bond cannot be rotated, we will have to use another beta hydrogen. Let's take a look at what that means. So this is a more complicated case scenario. So for example, let's say I have a leaving group here, it's bromine. And let's say that I have a isopropyl here, and this is my hydrogen. So my leaving group is on a wedge, and my hydrogen on the neighboring carbon is on a wedge too. That means this hydrogen cannot work because they are on the same plane. They're both on a wedge. So what we will have to do is we will have to rotate around the single bond. So I'm going to show this rotation. I will leave my left side the same. I'm going to show my bromine on a wedge. And from my right side, I will push this carbon up. So now this carbon is going to be up, which means this methyl group is going to be down. Just imagine rotating around this bond. And when that happens, the stereochemistry here flips. Now, my hydrogen is going to be on a dash, and this group is going to be on a wedge. And now I can use this hydrogen. My base can come in, take the hydrogen. This bond can break, making a double bond, and this leaving group can leave. And so the product will be looking like this. This is my final product of this elimination. So even though this hydrogen was on the same plane as my leaving group, when after I rotated, I made sure that it was on the opposite plane, and then I could do my E2 elimination. Another example, let's say that I have a ring, and let's say that, again, this is bromine, and let's say that this is a methyl group here. That means this hydrogen on the carbon, neighboring carbon with the leaving group, is on a wedge. I cannot rotate around the ring. I cannot rotate a single bond inside the ring. So I cannot use this hydrogen. I will have no choice but to go to the other side, and the other side carbon has two hydrogens, and I'm going to use one of them. So these are some of the tricks you just have to remember when dealing with E2. The hydrogen and the leaving group must be opposite. Let's continue. For E2, we want to make the most substituted double bond whenever possible, which is called Zaitsev rule. So what does it mean? Let's say that my leaving group is here. Let's call this a leaving group. Which hydrogen would I want to use to make a double bond? Would I want to make a double bond here or here? If you look at this neighboring carbon, it is primary. It's attached to one carbon only. This carbon is secondary. It's attached to two carbons. If I use a hydrogen from this carbon, which is the more substituted carbon, I will make the more substituted double bond. So this double bond here, if I make it, it will be disubstituted, attached to two carbons. But if I make a double bond here, it will be monosubstituted. So I want to make, whenever possible, the most substituted double bond possible, which means I want to take off hydrogen from the most substituted neighboring carbon. I want to make the double bond between the carbon that had the leaving group and its most substituted neighboring carbon, the carbon that's attached to most carbons. In this case, it would be the carbon on the right, not on the left. So that would be the major product. And I could make a double bond with the left carbon, and that would be my minor product. However, we do have to consider that if we have a bulky base such as third butoxide is OCH3 minus. It can be also shown as this. A lot of times it's shown together with Na or K. This is minus, this is plus. If you see this molecule, you will do most likely Hoffman elimination. Most textbooks and professors will tell you that if you see this molecule, this is a strong, bulky base, and it will want you to create the least substituted double bond. So you will take the hydrogen from the least substituted neighboring carbon to make the least substituted double bond, which is Hoffman. In terms of reagent, we want to use a strong base. Usually it's OH minus or RO minus. All of the reactions we are talking about, SN1, SN2, E1, and E2, all of them want a good leaving group. If we do not have a good leaving group, we cannot do any of these reactions. Rearrangements are not possible, and this is another example. I have a strong base. This is my beta hydrogen on the carbon next to my leaving group here. And my strong base will take the hydrogen, the bond between hydrogen and carbon will break, making a double bond, and then the leaving group will leave, and this is my final product. So this is E2. Again, E2 is concerted, it all happens at the same time. Now let's look at E1. E1 is a two-step mechanism similar to SN1. The first step for both is the leaving group leaves, creating carbocation, and that is the rate limiting step. So here I show the leaving group leaving, creating carbocation. Step number 2, my nucleophile or weak base attacks the hydrogen on the neighboring carbon. Again, it's not going to be shown to us. You will be the one showing that hydrogen. You will look at the carbocation and you will identify the two carbons that are neighbors, so 3 carbons that are neighbors, and you will show the hydrogen on one of them. Base will take that hydrogen, the bond between hydrogen and carbon will break, creating a double bond, so 2 more arrows. We can make either cis or trans double bonds, and trans is more stable than cis, so trans will be my major product. We can also make more or less substituted double bonds depending on which neighboring hydrogen we use, and we always want to make the most substituted double bond whenever possible, which is Zaitsev rule. In terms of stereochemistry, because we're going, I'm sorry, not stereochemistry, in terms of the substrate, because we're going through a carbocation, we want the best carbocation possible. So this reaction would prefer tertiary, okay with secondary, and would not do primary substrates. For the weak base, it's usually neutral, weak, similar to SN1. We use water or alcohol. For the leaving groups, all of them want as best of leaving group as possible. Rearrangements are possible, which we will cover in another video. And this is an example. I have a weak base and I have my leaving group here. Leaving group leaves, creating a carbocation. Then water attacks the hydrogen. That bond between hydrogen and carbon breaks, making a double bond. And my major product is trans double bond. Now, let's see. Let's put our knowledge to the test. Let's do two reactions. We will see whether they are E1 or E2, and we will try to predict the product. Let me just create it. So let's say that I have Cl here, and let's say that I have a methyl group here, and let's say that my reagent is OH minus. So first I say I have a good leaving group. Let's say good leaving group. I identify that I have a good leaving group. OH minus is a strong base. I have a strong base. And in another video, I will definitely show you the chart where I compare all of the reactions SN1, SN2, E1, and E2, so you can easily predict which one you're doing. But so far, we will just focus on E1 and E2. I have strong base. Who likes strong base? E2. So right away, if I have a strong base between E1 and E2, I know I am doing E2. I have my leaving group. Now I have to find my hydrogen. So I look at the two carbons neighboring the carbon with the leaving group. This is one, this is another. And I'm going to show the hydrogens on them. Because this methyl is on a dash, the hydrogen here is on a wedge. Here there are two hydrogens, which means one on a wedge and one on a dash. Next, I say, what can I use? Preferably, I would like to use this carbon because it's more substituted, it's attached to more carbons. But because this hydrogen is on a wedge and this chlorine is on a wedge also, I cannot use it. I cannot use this carbon because I cannot make this hydrogen go on a dash, be opposite of chlorine stereochemistry. So I have to use the other one. Remember, in this reaction, the arrows are leaving group leaves, base takes the hydrogen, and the bond between hydrogen and carbon breaks, making the double bond like that. And so my product will be a double bond here, and I still have the CH3 there. So that's my product for E2. Now let's go ahead and do another reaction. Let's say that I have an iodine here, and let's say that my reagent is water. So I have a good leaving group right away. That means I can do SN1, SN2, E1, or E2. And I have water, which is a weak base, weak nucleophile. And between E1 and E2, that means I will be doing E1. I will also be doing SN1, but for now, we will just focus on E1 and E2. In E1, how many steps is it? It's 2 steps. Step number 1, leaving group leaves, creating carbocation. So we will show leaving group leaving. And the carbon that had the leaving group will now have a carbocation. Now, I'm ready for the step number 2. Step number 2, I find the beta hydrogen. Again, I look at the carbocation and I look at the 2 carbons or 3 carbons that are neighbors of this carbocation. In this case, I have left and right. The left one is only attached to 1 carbon and the right one is attached to 2. This one is more substituted, so this is the one that I would like to use. This is the one whose hydrogen I would like to use. So I'm going to show hydrogen there, and I'm going to show my water taking this hydrogen and making the double bond, and my major product will be trans double bond here. Again, I will also make other minor products. I could make a double bond with the least substituted carbon. I could also make a double bond cis, but my trans double bond would be the most substituted one. And let's do just one more example here. Let's say that I have BR, and let's say that I use this. So first, I look at this and I realize that this is terbutoxide. Anytime you see K, Na, or Li, those are spectator ions. Give them a plus and don't pay attention to them. The second part will have a minus. So what is this? That's terbutoxide. For most professors, they will tell you that terbutoxide is a very strong bulky base and it will make the least substituted double bond. This is E2. Anytime I see terbutoxide, I know I am doing E2 elimination. And again, most professors, not all, so depending on your textbook, will tell you that it will do Hofmann elimination. So what I'm going to do is this carbon has 3 hydrogens. One will definitely be on opposite stereochemistry. I will go ahead and show opposite stereochemistry dash, and I'm going to make my terbutoxide take the hydrogen from the least substituted carbon. Between these two, it's the left one. Left one is only attached to 1, right one is to 2. Make the double bond, make the leaving group leave, and my product is Hofmann product, Hofmann elimination, where we make the least substituted double bond.